Okay, we want to start with kind of talking about the lab that we just did with melting ice and freezing water. But first off, we're going to talk about what is the system and what is the surroundings. The system is our focus. Our focus is whatever we're looking at specifically. So we would have been looking at the water, and then we would have been looking at the ice as it was melting. The surroundings is everything else. So in our example, we had ice, let's say in a test tube. We were not looking at the test tube, we were looking at just the ice that was within the test tube. So the test tube would consider to be the surroundings. So if we had our ice, we're going to draw the particles drawn, fused together like this. This is my system. I'm going to do a circle. We'll show you that later on the LL diagrams. In this one, we had to have heat enter the system. So heat was transferred into the system. And so the system was our ice. When it was transferred in here, it weakened the attraction between the particles. So that means these particles then were not fused together as much. They could flow over each other. So it weakens that attraction for them. So we're just looking at when it changes state. So the reverse is when we had a fluid, so we had our water, our system here would have been the water. The reverse happens. Energy is transferred out of the system. And our energy is heat. When energy is transferred out, the particles fuse back together again. So this strengthens the attractions between the particles. So that's the difference between the two. So we've got heat energy going in the system or heat energy leaving the system. So for us, heat sometimes can be represented with a capital letter Q also. So in other words, when we talk about heat, this is the energy that is transferred from the hot object to the cool object until it reaches thermal equilibrium. When it reaches thermal equilibrium, that means that the transfer between the two objects is equal. The units for this are either a joule, notice it is capitalized, it is named after a scientist, or we could use calorie. This is what they used initially, was a calorie. There's a conversion factor between the two, and it is 1 calorie is equal to 4.184 joules. So we want to look at two processes, endothermic and exothermic. And we're going to look at the ice melting, which is endothermic, meaning heat. Thermic is heat going into the system. Exo means heat leaving the system. So if we did an energy description here, so I'm going to say this is my system, so this is the ice. Endo, we have heat, energy going into the system. Exo would be energy leaving the system. So that would be our two different things. So we're going to say heat is absorbed here. Heat here is released. So that would kind of define those two or different things. Now, if we wanted to write an equation for this, so we would say, since heat is being absorbed here, we would say heat plus A yields B. So in other words, this could be our ice for A, and B would be our water. So on the other one, for exothermic, we would say that heat A yields B plus heat. It's given off. So in other words, this would be our water, and then this would be our ice. Now, if we did an energy graph, it would look like this. So this would be energy, and this would be time. Now, it would look something like this. For the first one, if it's endothermic, it would be, I would have my reactants here, or we could say A, and at the end, I'm going to get my products, or we could say B. So this means heat is going into it, so the products have more energy than the reactants, because they absorb that heat. Okay, so this would be my ice here, and then this would be my water here. If I was to look at the other one, same kind of graph, time and energy. The only difference is I would start out with my reactants having more energy, so this would be A, and then over time, my products would have less, B. So this would look like, this is my water, heat is released, and this is my product down here, my ice. Okay. So that's how we would look at that. In these examples, Q, and notice it can be either uppercase or lowercase, is greater than 0 if it is endothermic. In the other case, Q is less than 0. So at the molecular level, what is happening? For the one that is melting ice, the attractions between particles are weakening. And we call these attractions intermolecular attractions. So these are between, in this case, molecules of water. So that's what's keeping one water molecule attracted to another water molecule. Okay. In the other case, it would be the attractions between particles are strengthening. So that would be intermolecular attractions are getting stronger. Now, I want to make a difference between these two. There's also called intramolecular. This would be the attractions between hydrogen and oxygen. in order to break those, you need a chemical reaction. We are not dealing with a chemical reaction. We're just dealing with a change in phase. So these intermolecular ones are dealing with a change in phase. Notice these ones, intramolecular, these are stronger than intramolecular because it would take more energy to break those compared to breaking intermolecular. So I did do a slideshow that shows you how to do these LOL diagrams, but I'm going to do a couple of these just on with you, just so that you get an idea. So the first thing is define the system. So our system here is this coffee. Okay? Need to do that first. Find what are we looking at? What is our focus? And it sits on the table, and we know that it's hot initially, and it is going to cool. Okay, so we're going to say this coffee is pretty hot, and then we had put parameters in the slideshow to say how much we were going to represent these. So it's not boiling, but it's hot, so we're going to go 3 bars. It's probably above 30 degrees Celsius. Okay, now the phase it's in, we said 2 bars was going to represent the phase. I do not like to do partial bars, so I try to stick with whole units. Okay, now in this case, when this coffee sits, so we're doing a snapshot when it's first on the counter, and then final is when we see it in, let's say, an hour later. It's still coffee, it's still a liquid, but now we know it's cooled down. We're going to say to room temperature. 2 bars is about room temperature. Okay, so another thing that we need to look at is energy has to be conserved. We haven't talked about this yet, but we are going to show conservation here. So whatever I start with, I have to end with. Okay, so I have 5 units over here of energy, and I only have 4 units here. I need to show where did that unit go? Well, didn't 1 unit, we can say, exit the system? Didn't this go to the surroundings when the coffee cooled? It went into the air around it. So this is an exothermic process. And if you look, I have 5 units here. Now I have 5 units here. So I do have conservation of energy there. Now, I want to look at another one. Water in a syringe boils when the volume of the syringe increases. So we're going to look at, this is a little different one. So in this one, we are going to say it's going to boil because of reduced pressure. If you decrease the pressure on something, it will boil because of that. It doesn't need to have a high temperature, so the temperature is staying constant. It is not changing. So the temperature is constant, and it boils because of reduced pressure. So what are we looking at? We're looking at this water in the syringe. That's my system. That's what I'm looking at, the water that's in the syringe. It's at room temperature. And we said here the temperature is staying constant, so my thermal has to be remaining constant. The next thing is, initially it's water. And when it boils, it changes to a vapor. So the phase, we said 4 bars is going to represent energy phase for gas, is going to this. If I look, I have 4 units here, and I have 6 units over here for energy, not conserved. So that means energy needs to be going into the system, and I need 2 more. It's going to look like this. This is endothermic. So now I have done one that was endothermic and one that was exothermic. There's a few more here for sample ones to do. I'd like you to do on your own. I will upload these to Schoology so you can check yours, and then do the worksheet that is on the next page, 3.1, with those examples, and I will also upload those answers for you.